All right, before we start today, I've been asked by AMSA, the American Medical Student Association, to pass along information about their second general meeting, which is tomorrow in SW 102, wherever that is. And AMSA is actually for pre-medical students, not for medical students, so don't let the name confuse you. They're going to have a meeting tomorrow. Today we're going to finish chapter 2, so as a reminder, the chapter 2, the first homework assignment, the deadline got extended until Wednesday night. So if you didn't see the email that I sent about that, I believe it's called C2 homework A, or something like that. That's going to be due Wednesday night, 11:59 p.m. So normally they're all due on Sunday, but we didn't quite finish everything last week, so that's why we gave you a little bit of extra time. The chapter 2 homework assignments are arranged in a very weird way because they seem to both cover all of chapter 2. So after today we'll be caught up, and then the next assignment will be due when it normally is supposed to be, which is next Sunday. So you'll have basically 2 assignments due this week. All right, so if there's any questions about that, let me know, but you'll have roughly 48 hours after class today to finish your chapter 2 attempts for the first chapter 2 assignment. And again, make sure you do the correct one if you're trying to beat the deadline, because chapter 2 homework A will close on Wednesday, and there's going to be 2 chapter 2 assignments open this whole week until then. Okay, so what we're going to do today is continue with what we left off last time. So last time we talked about the different types of orbitals. We talked about how to sort of understand some things about the relative energies of those orbitals. And so what we're going to do today is now figure out how to determine how many electrons each orbital or each subshell will have in a multi-electron atom. So we're going to do what's called electron configurations. And to do this, we have to follow a few rules. So the first one is called the Aufbau principle, Aufbau being a German scientist, as the name suggests. And this is referred to also, I don't think it was named after a person. I think Aufbau actually means building up. But anyway, it's a German term, but it means building up. And the idea with the Aufbau principle is that we're going to fill the subshells in order of increasing energy. So we're going to fill the lowest energy subshell first, then the next one, then the next one, until we have put all of our electrons in, however many electrons we have in that atom. Okay? So that's sort of what the principle is. What we have to learn, of course, which we're going to go through a lot today, is how to know what order the subshells come in. All right, so we're going to add the electrons one at a time. And we're always going to put them into the lowest available sublevel. Say lowest energy. It's probably a better way to say that. All right, so we're going to completely fill up one subshell before we move on to the next one. We're always going to go from lowest to highest energy. And so for any element on the periodic table, that ordering is the same. There's not different orders for different elements. There's a couple exceptions we won't need to know, but in general, we're going to follow this Aufbau principle of going from lowest to highest energy subshell when we add electrons. And that will give us then what is called the ground state configuration. So we know the definition of ground state from the Bohr model is the lowest energy position of the electron in a hydrogen atom, and for a multi-electron atom, the ground state configuration is the arrangement of electrons that also gives us the lowest energy. So those two terms are the same, basically, just here we're talking about more than one electron, obviously. And so this is going to be the arrangement of electrons into those sublevels. There's one that has the lowest possible energy. All right, so basically if we follow the Aufbau principle and one other rule that I'm going to give you on the next slide, that arrangement of electrons that results from following those rules will be what's called the ground state electron configuration. And the way that we write this configuration, the way that we abbreviate it, is we're going to write each sublevel that has electrons in it. We don't leave out the empty sublevels, but each sublevel that has electron in it is going to be written in the following way. So this is sort of a general abbreviation. And here's what the different terms mean. So X is going to represent the superscript, is going to represent the number of electrons that are in that sublevel. So for each sublevel, we're going to designate how many electrons are in there in the configuration. N is going to be the first quantum number, the principal or shell number that designates that sublevel. So remember that a sublevel is designated by an N and an L value. So we're designating them in this way, but again, the L part of it is not going to typically be a number, it's going to be SP, D, or F. So each subshell is going to be labeled as we'll see, 1S, 2S, 2P, 3S, 3P, and so on. And then these numbers that are attached to those are going to tell us how many electrons are in each of those sublevels, again, working our way from lowest energy to highest energy. So that's how we write the ground state configuration, and again, if we follow the rules that we learned today, we will be able to easily predict those. All right. Now, to know the ordering of the sublevels, there's a couple ways to do this, and there's a good chance in high school or any other chemistry course you take, you might have learned the little, the diagonal diagram. You've probably seen this before, where I don't even know if I can draw it right, but it's like 1S, 2S, 3S, and 2P, and then you draw these diagonal lines through it and so on. I'm not going to try to do that because I don't know how to anymore. I used to probably when I was your age, but not anymore. So the way that you really want to do this, and that I encourage all of you to learn how to do, is to use the periodic table to tell you the ordering of the subshells. So we're going to start learning now about how the periodic table is organized. It's not just a random arrangement of elements that are just in numerical order. Why does it have this specific shape, this specific arrangement? And basically what you have in the periodic table is that each section of the periodic table that I'm going to block off here represents a different subshell, okay? So let's do different colors to designate these. So the first thing is that each row of the periodic table represents a value of n, a shell number or a principal quantum number. So the first row is n equals 1, n equals 2, 3, 4, 5, 6 is, and I guess 7, but 6 is really as low as we'll go. So those are going to be the different n values, each row of the periodic table represented by a value of n, and then sort of sections of columns of the periodic table, different columns of the periodic table represent the different sublevels within these shells. So if we go to the first two columns here, which I'll highlight in blue, or try to highlight anyway, that's going to be the NS subshells. So and then there's one more that is kind of out of place. Helium is also an S element. So basically, if we're in this part of the periodic table, it's n equals 2, and this is the S, so this would be 2S, 3S, 4S, and so on. So that's what we call the S block. If we go over to the right side of the periodic table, and also remember, we talked already about some of the rules. So if you're in an S subshell, L equals 0, that means M sub L can also only be 0, which means you only have one orbital, a maximum of 2 electrons. And so that's why this S block of periodic table is 2 elements wide. It's only 2 electrons you can put into the S subshell before you have to move to the next subshell. So that's why there's 2 elements in these columns. If we go to the far right of the periodic table, this whole block here, these 6 columns on the right, these are going to be, I'll do it, sorry, let me do it in red so it's not confusing. This whole part is the P block, as we call it, NP, okay? Kind of reminds us of, I guess, a prison arrangement. You have S block, P block, D block, and so on, but this is, in this case, subshells that we're talking about in the range on the periodic table. So you have NP over here, so as we go through these elements, you're going to be in the P subshell, again designated by the value of N that corresponds to the row. So the first P subshell, as we know, is 2P, so that starts here, 2P, and then there's 6 elements that we can have in that block because there are a maximum of 6 electrons that can go into a P subshell. All right. We also have in the middle part, my favorite part of the periodic table, as it turns out, this one here. Sorry, let me get the thick one to highlight those. I'll do them in columns just to stay consistent. So these 10 columns here in the middle, this is going to be our D block. But one important thing about the D block is that, so again, these 10 columns here, it's not ND, it's going to be N minus 1 D. So when we're in the 4th row of the periodic table, as we go through this set of elements here, that's N minus 1 D, so that's actually 3D. We know that the first D subshell from our quantum number rules is 3D, and that starts here. So actually 4S comes before 3D. That's really the first place where the principal quantum numbers don't tell you the order. And then this is going to be 3D, 4D, and 5D as we go through that part of the periodic table. And then the ones that we won't do a lot with, but I want to make sure that we include them for completeness, is going to be these ones down here. So there's 14 elements that are separated out. The only reason they're separated is just to make the periodic table a more reasonable aspect ratio. They're cut out from these two rows here, but these are going to be, and we're not going to do a lot with these, as I said, but these are going to be the n-2 F blocks. And this one starts at atomic number 58, so it comes from the 6th row of the periodic table. So this is n-2, which is 4F. This one starts at atomic number 90, comes from the 7th row of the periodic table, so this is 5F. We're going to have some electron configurations we deal with where the 4F subshell is completely filled. We're not going to be dealing with electron configurations within the F block because there's just too many exceptions, too many things that are hard to predict within these elements. But we want to know that this is the 4F. So basically when we're going through and doing an electron configuration for any element, we're going to go in order of atomic number, 1, 2, 3, 4, and so on. And we're going to add electrons to these subshells until we get to the element that we're interested in. So let's see how to do that. But before we do that, we want to give one more rule that doesn't really change the appearance of the electron configuration, but if we want to start talking about the quantum numbers of individual electrons, or in particular the spins of the electrons, we have to be aware of Hunds Rule. So a lot of times for an electron configuration, we don't even need to consider this if we're just talking about how many electrons are in each subshell. But if we want to start talking about how many electrons are in each individual orbital, or what is the spin of those electrons, are they plus 1/2, minus 1/2, and so on, we have to understand what's called Hunds Rule as well. So the Hunds Rule applies to degenerate orbitals. So we said degenerate orbitals are orbitals that occur at the same energy. So within each p subshell, you have 3 degenerate orbitals. Within each d, you have 5 degenerate orbitals. So those are going to be the places where this rule is especially important. But when degenerate orbitals are filled with electrons, so the question is, do we put 2 electrons in each orbital at a time, or do we put 1 electron in each orbital and then start doubling them up? That's really what this rule deals with. And what we're going to do is we're actually going to fill each orbital individually before pairing up electrons. So we're going to first put 1 electron in each orbital. And the other important thing is that when we do this, all of those electrons need to have the same spin. It doesn't matter if that spin is up plus 1/2 or down minus 1/2. By convention, we do them all spin up first, but it's either way is acceptable and equivalent. But you're going to do each electron with the same spin, 1 electron per orbital. Only after you've filled each orbital with 1 electron will you start pairing up 2 electrons in the same orbital. A simpler way of saying this, if we're familiar with this terminology, is that we want to maximize the number of unpaired electrons. So an unpaired electron being an electron that has spin up but does not have a second electron with spin down that basically is paired with it. So we want to maximize the number of unpaired electrons. But this will make more sense when we do some examples. So when it matters, as we said, is in degenerate subshells. Which on the periodic table is just going to be P, D, and F subshells. Really, for our purposes, just P and D, because we're not going to really do partially filled F subshells. And if you want to know why this is, the real answer is very quantum mechanical in nature, and our understanding of quantum mechanics is still at a fairly basic level in this course. But it's a quantum mechanical parameter called exchange energy that you're maximizing when you have electrons all arranged with the same spin. Another way of thinking about it that's also valid and perhaps simpler is that it minimizes electron-electron repulsions. This especially helps us understand why would we put 1 electron in each orbital before pairing them up. Because if you put 2 electrons in the same orbital, those 2 electrons are occupying the same region of space and they're going to repel each other more strongly. If you put 1 electron in each orbital, they can spread out a little bit more and they don't interact as much. That's part of it. The other part of it, which is why the spins are the same, is what's called exchange energy beyond the scope of this course. But there's basic quantum mechanical reasons for this, but we're just going to learn what this rule is and how to follow it as we do electron configurations. Okay? So let's go through some electron configurations. We're going to start not with the very easiest ones, but some that are not too bad. Let's start with boron and carbon. So we're going to do two things here. We're going to write the electron configuration, and then we're going to indicate with arrows how many electrons go into each orbital and whether those electrons are spin up or spin down. Okay? So if we go to the periodic table and find B, which is boron, it's going to be here. Give me a second to open up the periodic table. All right, so what we're going to do is, as we said, we're going to go through the different blocks of the periodic table one by one until we get to the element we're interested in. So we're going to try to find the electron configuration for number 5, which is boron. And we always start at the beginning and go through each part of the periodic table one at a time as we go through that. So we're starting here in the first row. This is 1s. Remember, this is 1s1, 1s2. 1s2 is way over here for reasons we'll get into later. And then we go to the second row, which is atomic number 3. That's going to be 2s, 2s1, 2s2 to get to beryllium. And then jumping over here to boron, which is where we stop, that's in the 2p part of the periodic table, and that's going to be 2p1. So we go through the subshells one at a time. 1s, 2s gets filled, and then we stop here at 2p1 because it's the first element in the 2p block. Okay? So the way we would write that configuration in its full form is going to be 1s2, 2s2, 2p1. If you're doing problems like this on the exam, typically you're going to be selecting from a set of multiple choice answers. The first thing you should always do when you're trying to identify an electron configuration is make sure it has the correct number of electrons in it. So if boron is atomic number 5, and we're talking here about boron with no charge, that means it has 5 electrons also. So your configuration 2 plus 2 plus 1 should have 5. If it doesn't, then don't choose it as your answer. That can't be right, okay? But this is the correct arrangement of those 5 electrons, 1s2, 2s2, 2p1, again following the order in the periodic table as we go through. If we want to put those electrons into individual orbitals, we will recall that each of the s blocks just has a single orbital in it, and the p block has 3 orbitals available. And then the way we do this is we use upward arrows to indicate spin up, or plus 1/2 for m sub s, downward arrows to indicate spin down, or m sub s is minus 1/2. So in the 1s block, we have 2 electrons. They're going to be arranged like that, 1 up, 1 down. Anytime 2 electrons are in the same orbital, remember, 1 has to be spin up, 1 has to be spin down. 2s, same thing, there's 2 electrons there. Now when we get to the 2p, we actually have a lot of choices here because we just have 1 electron to put in the 2p orbitals. Does it go here? Does it go here? Does it go here? Does it go spin up? Does it go spin down? The real answer is it doesn't matter. All those are equivalent, whether you put the electron, remember all 3 of these orbitals are the same energy, spin up and spin down is the same energy, so if you have 1 electron in a set of p orbitals, it doesn't matter where you put it. You could put it here, that's fine. You could put it here, that's fine. You could put it there, or you could do any of those 3 places spin down, and all of those would be equivalent configurations. Okay? So when we're following Hunds Rule, the important part is that just 1 electron in the orbital, and it has to, and it doesn't, in this case, doesn't matter what spin it is because there's only 1 electron. Yeah.
Excuse me, is this 7b, 7b or 7b? I thought it was 7b, right?
Sorry.
Is this 7b?
7b.
7b.
B is number 5. B is boron, which is the atomic symbol.
No, that one on the square. No,
Those are arrows. So we draw half arrows basically to. You could also, some people do full arrows like this. It's just faster for me to draw half arrows, so that's what I do. So that's an up arrow and a down arrow indicating each electron. So each of these arrows indicates a single electron. And that's how we write them out. And then the last one, as we said, we have a choice. Now, conventionally speaking, if you just want to sort of follow a convention and not have to think about it too hard, we usually we go from left to right, and we start with spin up. So most often you would see this configuration, if we want to include the electrons individually, written like this, where you fill the first p orbital and you have a spin up electron instead of spin down. Like I said, in reality it doesn't matter, so if you're asked to identify the ground state configuration, any of those possibilities with this 1 electron being in any of these 3 orbitals with either spin up or spin down is equivalent. Okay? A lot of background noise, hard to concentrate. Okay, so let's go to carbon, which is the next one. Z equals 6 element on the periodic table. So carbon is right next to boron, so we're going to have the same electrons first. We're going to have 1s2, 2s2, we go to 2p now, 2p1, 2p2 takes us to carbon here. So this is the second element in the 2p block, so it's going to be 2p2. So the configuration is not too much different. It's just going to be 6 total electrons, and there's going to be 2 in each of those subshells, 1s2, 2s2, 2p2. The difference with carbon is that if we're going to write the full configuration including the spins, here's where we have to be mindful of Hunds Rule. So we're always going to fill up one subshell before going to the next. We're never going to skip, but we're going to still do 1s2, 2s2 like we did before. When we get to the 2p subshell, now we have a few choices of how to arrange the electrons. And what Hunds Rule tells us is the 2 things that are important is that they need to be in 2 different orbitals and they need to have the same spin. So again, the conventional way to do that is to write it like this. You populate the first 2 orbitals, each with the same spin up. But any combination where the 2 electrons are in different orbitals with the same spin would be fine. So we could do that, we could do that, or we could do any of the spin down combinations. And technically those are all equivalent. Conventionally, you're most likely to see it like this, but we do want to be aware that there's more than one way of writing that. But again, the rule is 2 different orbitals, same spin for the 2 electrons is what's key. All right, any questions on those simpler ones? Now, another thing we're going to want to do at times is for heavier elements, for elements that have more electrons in them, you might imagine it can start to get tedious to write out every single subshell. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and so on. Like, it gets a lot to write and a lot to say. So if we go to the heavier elements, the ones that have higher atomic numbers, there's a shortcut that we're going to use for this. So if we did Na, which is sodium, if we want to do the full thing, we can. This one's not too bad because it's only 11 electrons. But the full configuration for sodium, we start at the beginning and work our way up to 11, which is Na. That's where we're going. It's going to be 1s2, 2s2, then we go to the 2p block, 2p1, 2, 3, 4, 5, 6. And then to get to Na, that's in the 3s1. So it's going to be that configuration. So if we write that out, that would be in its full form. 1s2, 2s2, 2p6, 3s1. Now typically what we do, and we're going to talk about this a little bit more later on today, but what we're going to do is these inner electrons, these subshells that are all filled, so the 1s subshell is completely filled, the 2s subshell is completely filled, the 2p subshell is completely filled. This is what's referred to as the noble gas core. So this, basically what you do is you're going to abbreviate this. This is the same configuration as neon, which is Z equals 10. So if we go back to the periodic table, we basically went to Ne, which is neon, and then we just added one more electron to get to sodium. So what we often do for these heavy elements is we go to this column of the periodic table, the element that comes before it, what's called the nearest noble gas. So Na is number 11. The noble gas that's closest to it is neon, Ne, and we're just going to abbreviate those first 10 electrons with just that symbol Ne. Because basically, again, that's a completely filled 1s, 2s, and 2p subshell. And so what we're going to do is we're going to abbreviate these 10 electrons with just a bracket sign and the symbol Ne, indicating that we have that electron configuration, the 10 electrons for neon, plus this last one here, which is not part of that 3s1. Okay, so basically the nearest noble gas being the last column of the periodic table, as we'll touch on a little more in detail in a little bit. This nearest noble gas, which are what we call the inner or core electrons, are going to be indicated with brackets. Okay. And then if we're in magnesium Mg, let's do one more. So in this case, if we don't want to write the full configuration, what we can first do is find the noble gas that's closest to that. You go before it, of course. So Mg is number 12. The noble gas that comes immediately before that is still Ne, number 10. So we can abbreviate those first 10 electrons with Ne in brackets. And then we go to this part of the periodic table to get to Mg. It's going to be 3s1, 3s2. So very similar to the last one, but we would just write it as Ne for the 10 core electrons, and then the last 2 go into the 3s2. All right. So there's two reasons for writing configurations like this. One is that it is a time saver, because we don't have to go through every single subshell, especially for, if we get to atomic numbers of in the 50s and 70s and so on. Like, that's a lot of electrons, a lot of subshells to have to write out individually. So writing this core noble gas configuration as an abbreviation is helpful. The other thing that allows us to do is identify quickly what are called the valence orbitals, or the valence electrons, which would be the electrons in those orbitals. And valence electrons basically means the outer electrons. the ones that are furthest away from the nucleus. So, and as we'll learn more as we go throughout this course, these are the most important electrons because these are the ones that participate in chemistry. So if we're doing chemical reactions with elements, if we're forming compounds, these valence outer electrons are the ones that are involved in those chemical reactions. The core electrons, the ones that are buried close to the nucleus, they're going to stay there. They're going to be held tightly by the atom at all times. So we want to be able to count what are called the valence electrons. And first we're going to learn how to do it for main group elements. So main group elements are the elements that appear in the S or P block. So they're either in the first 2 columns of the periodic table or the last 6 columns of the periodic table. That's called the main group. Again, these periodic table classifications we'll go through in more detail in a second. But for these main group elements, the valence electrons are going to be the electrons that have the highest principal quantum number, and that's going to count both S and P. All right, so that means for elements in the S block, the valence electrons are going to be just however many S electrons it has, either 1 or 2 in all cases, because that's all you can have for the S block. If the element is in the P block, the valence electrons are going to be the S electrons plus however many P electrons it has. All right, there's also a shortcut for getting this for main group elements, which is to look at these Roman numerals on the periodic table, these group numbers. That tells you how many valence electrons there are. So if we're in the first column of the periodic table, which is group 1A, that means there's 1 valence electron. It'd be the S electron, the last S electron that we put in. In group 2, there's 2 valence electrons. It'd be the 2 last S electrons that we put in. Over here, if we go to the P block, 3, 4, 5, and so on, we have 3, 4, 5, 6, 7, 8 valence electrons, which would be these 2 S electrons plus the P electrons that we add as well to finish out the configuration. So it's always going to be either 3 or higher for those. Okay, so we'll talk a lot more about valence electrons going forward, so we're going to definitely come back to that more in the future. The last thing we want to talk about is electron configurations for transition metals, which is not really any different. We just have to remember the key point is that in transition metals, we're talking about the elements that are in the middle of the periodic table, the ones that are in the D block as we called it. And we have to recall that in this part of the periodic table, the NS subshell, whether it be 4s, 5s, or 6s being the appropriate ones for this argument, that's going to be filled before the n-1 D subshell. So 4s is filled before 3D, 5s is filled before 4D, 6s is filled before 5D. Again, if you remember the arrangement of the periodic table, that comes directly from that because that middle part of the periodic table is the D block, but it's n-1 D, so you take off 1 from the row of the periodic table. And then when we're counting valence electrons for transition metals, it's going to be all of the S electrons, so there's going to be typically two S electrons in most transition metals, and all of the D electrons that are in the highest subshell. The highest subshells, I should say. So all transition metals basically have 2 valence electrons from the S plus however many D electrons they have in their valence configuration. So if we do an example of an electron configuration with OS, osmium, so this one's about as complicated as they get for the types of elements we'll ask you about. So this is a pretty far down in the periodic table. So if we go to OS, which is going to be over here, number 76, if you have trouble finding it. So especially since it's so far down in the periodic table, we're going to want to use the abbreviation with the noble gas. So we're going to find the noble gas that comes before this. So we go backwards over here. So we're going to abbreviate the first 54 electrons with just XE in brackets, indicating that those 54 electrons fall in that configuration. After there, to get to osmium, we have to make sure we don't skip anything. So from there, we go down to here. This is the 6th row of the periodic table. So it's going to be 6s1, 6s2. But then from here, we're going to skip down to the 4f block. So it's going to be 6s1, 6s2, and then we have 4f, because this is 58. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 4f14, then back up to the D block. which is going to be now our 5D. So it's going to be 5D, 1, 2, 3, 4, 5, 6, and then we stop here at OS, which is where we stop. So 5D6 will be the last electrons that we put in. So for this last row of the transition metals, starting here at 57 and then going on to, or I guess starting here at 72 to 80, you're going to also have to make sure you fill these f orbitals as well. So the way we would write that then is going to be, as we said, the noble gas closest is xenon, Xe, so we put that in brackets. We went through the 6s2 first. We had to go through all 14 of the F elements, make sure we didn't skip any because we're going in numerical order. And then finally we got to 5d6. All right. Now there's a little bit of confusion, like do we fill the F or the D first in some cases? If we go back to that, you'll see that number 57 is technically a 5D element, and then it goes down to the 4F at 58. But for any of the transition elements that come beyond 57, which is what we'll have you deal with, you have to make sure you remember that we fill the 4F block before. Otherwise, you won't have enough electrons, because if we left out those 4F electrons, there wouldn't be enough. Remember, this has a total of 76 electrons, so this is 54, plus 2 is 56, plus 14 is 70, plus 6 is 76. If we didn't include the F electrons, we wouldn't have enough electrons at all. So we have to make sure we don't forget about those for the last row of the transition elements. That's why I did this one. So this will be the full configuration for OS, osmium. The number of valence electrons, though, is just going to be the S and the D. We don't count F electrons as valence for these. So it's going to be 8 valence electrons. So for transition metals, it's just the last S and the last D electrons that you put in count as valence, nothing else. So none of the core electrons and none of the F electrons as well. And then to fill out this configuration, we have a filled 6s, so we're going to put 2 electrons there. For F14, we would fill as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Again, they're all filled as we said. So all the electrons are paired in there. And then when we go to 5D, we have 6 electrons, so we have to make sure that we follow Hunds rule to maximize the number of unpaired electrons. So we're going to do 1 electron at a time with the same spin, so we're going to go 1, 2, 3, 4, 5. The 6th one has to be paired up with one of these other ones. In reality, it doesn't matter which one, but by convention, we go back to the first one and put it like that. So this will be the correct arrangement of the unpaired of the 5D electrons, and that leaves us with 4 unpaired electrons. All right, these 4 here, the last 4 that don't have a spin down electron paired with them, are going to be our unpaired electrons. There's a lot of valid ways to arrange these 6 electrons. By convention, this is how we would do it. We would put 5 in first, and then we would pair the last one in that first orbital. Okay. All right. So, any questions on electron configuration so far? Just using the periodic table. It's one of those things you're going to have to practice a lot. So if you don't follow everything now, that's okay. But hopefully that gives you a good introduction, and the more you do this, you'll get more familiar. Yes. Why isn't it 5F? Because as we go down, for the elements that we'll have you deal with, you're not going to use 5F, because the only time you would use 5F is if we're either in this row of the periodic table, which we're not going to have you do electron configurations for those, or if you come down to these elements here, but those are artificial man-made elements, so again, we're not going to really have you deal with those. So you guys probably won't use 5F in any of your electron configurations. You should be aware that this is the 5F row down here, but it's not likely to come up in any of your configurations because we don't have you do anything really beyond number 86 here is probably the last one we would have you do. Okay? Any other questions? Yeah? That's just the definition of valence electrons for transition elements. So whichever row of the transition series you're in, whether it's this row here, or this row, the valence electrons are given by basically the S and the D electrons. You don't count F electrons, you don't count any of the core valence or the core electrons that came before that. You can also get a number of valence electrons here in some sense from these group numbers, but they're not perfect in this case. So these numbers, the B groups, are sort of related to valence electrons, but it kind of breaks down at the end because the original people that made the periodic table didn't quite get it right. But it would basically be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, up to 12, and if you get all the way to this column here. So it's the S plus the D for all transition elements, but none of the F electrons if you have them. Yeah?
In workshop, we had a problem where we borrowed from the S subshell before doing the D. I think for chromium.
Yeah, so the question was, in workshop we had a problem where we borrowed from the S subshell and go to D for chromium. If you look ahead to the next slide in your notes, we're going to cover that. So thank you for preempting me on that. Any other questions on this before I move on to that? Yeah? So the question is about the 4F subshell. Why is that filled in this case? So we're going to go in numerical order. So when we get to, now technically speaking, the way this periodic table is set up is a little bit weird, but we go to here, which is, so we go to the core electrons, which is 54. Then we're going to number 55, which is 6s1, 6s2. 57 would technically be 5d1. But then after 57, we have to jump down here to get to 58. So we don't want to skip any elements in the series. So we go from 57 to 58. Going from 58 to 71 fills up the 4F subshell. Then we come back up here to 72 and go do the rest of the D electrons, 2, 3, 4, 5, 6 to end it up. So you have to make sure you don't skip any numbers as you're going through all the different blocks of the periodic table. All right, I think we should move on. So if there's any other questions, I'll handle them after class. And the question that came up just a little bit ago was about exceptions to this, and there's way more than this. So we're going to only have you guys know 2 exceptions. For every other element on the periodic table, just use the periodic table to predict the configuration, which in most cases is correct, but likely in some cases won't be, especially for the heavier elements. But there are 2 that we want you to know. The first one is chromium. So let's use the periodic table to predict the configuration for chromium, Cr. All right, so that's going to be argon are the core electrons, Ar. We go to 4s1, 2, and then 3d, 1, 2, 3, 4 takes us to chromium, Cr. So we would predict that it's going to be this configuration. But that turns out to not be quite right for chromium, and this is one of the exceptions we want you to know. So what actually ends up happening here is that the 4s and the 3d subshells are very close to each other in energy. They're not that far apart at all. So, bumping one electron from the s to the d is not that difficult to do. And what you end up doing in that case is you maximize the number of unpaired electrons. So if we take one electron from the s orbital, bump it up to the d orbital, we have more unpaired electrons, and so it's actually favorable to do that. So this is the wrong configuration. The actual configuration is same number of electrons. We're not changing the number of electrons. We're taking one of the 4s electrons and moving it up to the 3d to get this configuration here. Another way to think about this is that half-filled subshells are favorable. Well, in this case, you can't easily predict it from the periodic table. So this is an exception to what the periodic table predicts. The periodic table predicts this configuration up here, 4s2, 3d4. 4s and 3d being 2 consecutive subshells that are very close in energy. So it ends up, in this case, for reasons that are complicated, but so we're not going to go through them in detail, it ends up being more favorable to take one of these s electrons and promote it up to the d. So instead of s2d4, it becomes s1d5. Still 6 total valence electrons, but the arrangement is slightly different now. Okay? And then if we go to Cu, which is copper, we have a similar situation. The predicted configuration is going to be, we have still the same argon core. If we go and find Cu, it's over here on this side of the D block, so it's going to be argon core, 4s2, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9 takes us to Cu. Okay? So we predict this configuration, through 4s2, 3d9, but again, that's not quite right for us. So the actual configuration is once again to do the same thing. Take one of the s electrons, bump it up to the d subshell, and we get 4s1, 3d10. Okay? So instead of s2d9, it becomes s1d10. We take one of the electrons out of s, move it up to the d. In this case, again, for reasons that I probably couldn't even give you a solid explanation for, if I'm being honest, the filled d subshell is favorable. In this configuration, we have a choice. We can either fill the s subshell, have it 4s2, 3d9, or we can fill the d subshell, which is what's actually preferred in this case, 4s1, 3d10. The reasons for that are complicated from a quantum mechanical standpoint, so we're not going to try to explain them, but this is what you would end up being. So for these two elements, you need to know that the predicted configuration for the periodic table is not quite right, and we want you to know these two exceptions, and that's it. Another reason that we don't give you a lot of or any configurations from the F part of the periodic table is because in there it's more exceptions than rules. I mean, there's exceptions all over the place down there. But for the first 36 elements in particular, which is what we're going to mostly test you on, those are the only two exceptions we want you to worry about. Okay, so that sort of takes us to the end of electron configurations, and I believe that's also mainly the end of chapter 2. So as we sort of transition into the third chapter, this might still be chapter 2. I don't remember now. I don't read the textbook as often as I should. You guys should read it more than I do. I had the same slide twice, so skip that, sorry. We're going to go here to the slide that's labeled Periodic Table Overview. I accidentally had the same couple slides duplicated, so cross those out. We're going to go here to the periodic table. So what the electron configuration, one of the reasons it's important is that, as we're going to work through gradually, it helps us to make some predictions about how those elements will react with each other, what kinds of compounds they will form, how many electrons those compounds are going to have, and so on. And it also then allows us to categorize elements into different types, sort of based on their location in the periodic table, which sort of determines some of their key properties. So this is just going to basically just give us an overview of the periodic table, where we're going to classify things in different categories. So let's just go left to right. So the first thing we're going to do is the sort of grossest division of the periodic table is there's two types of elements. You have what are called metals and nonmetals. And the dividing line between those is a sort of staircase that starts here under boron, and you basically make a staircase that goes down the rest of the way. So anything to the left of this dividing line is classified as a metal, typically. Anything to the right is classified as a nonmetal. So we'll do the nonmetals first, because we're not going to really break these down in too much more detail. But so for the nonmetals, you're going to have everything here in these right columns. Now, some of the elements that are right on the borderline are going to be a slightly different category. So carbon, nitrogen, and phosphorus, oxygen, sulfur, selenium, and then all these last two columns. Those are all classified as nonmetals. Everything to the right is a nonmetal. Okay? Everything to the left is a metal, but there's a few that are on the borderline, which I'm going to put in next. So there's 6 elements that are classified as what are called metalloids. They're in between metals and nonmetals. So that's going to be boron, silicon, germanium, arsenic, antimony, and tellurium. So we're not going to really hold you to this too much, because depending on what source you read, some people classify different elements as metalloids. So we're not going to really have a strict division for our class. But these ones that are on the borderline right along this imaginary staircase that divides the periodic table, those are called metalloids. They're in between metals and nonmetals. Everything else that I haven't highlighted yet is classified as a metal. All the elements on the left side are classified as metals, but there's a few different kinds of metals that we want you to be familiar with. So they're not all just called metals. There's a few different categories. So basically what you have is these leftmost columns here. Let me get a different color, so I just use that one. All right, these leftmost columns here, except for hydrogen, I should point out that hydrogen is a nonmetal, even though it's in a weird spot. Hydrogen is a nonmetal. The rest of those in that column are going to be all metals. And those first two columns, and then so anything that occurs in the S block or the P block, that's classified as a metal. Bismuth and polonium. All right, so those ones there that are in the P block are classified as main group metals. All right, and again, we're not going to really hold you too much responsible for, is it a main group metal or metalloid, but anything that's in the S block is a main group metal. Any metal that's in the P block, starting with aluminum and on down and so on, those are all called main group metals. So they're metals, but they're in the either S or P block of the periodic table. Within those, there's actually a couple categories I want you to be familiar with that we'll get to in a second. And then the other types of metals you have are let's see, a different color here. This D block of the periodic table, those 10 columns, those are referred to as transition metals. So they're on the left side of the periodic table, they're all metals, but we call them transition metals when they occur in this middle part of the periodic table. They transition from the left to the right, if you want to think about it that way. So those are all called transition metals. And then the last ones, which are those F elements at the bottom that we're not going to do very much with in this course. I'm running out of colors here. These last ones down here, which I'll highlight, not really highlight, but cross out in black. Those ones down there, they have a few different names. They're called the inner transition metal. You'll also see that they call them lanthanide and actinide. That's a more specific term, but we're not going to get that specific in this class. And the only other thing that we want you to know are 4 columns in the periodic table have special names. So 2 of the metal columns, 2 of the non-metal columns. So the ones that are over here, except hydrogen, which is a non-metal, these ones are referred to as the alkali metals. All the metals in the first column. All the metals in the second column are called alkaline earth metals. And again, the whole reason we're doing this is that by categorizing elements into different, different groups, we can sort of understand a little bit about, their behavior, a little bit about their properties. And then the 2 non-metal columns, what you know is the second to last column here, starting with F and going down to AT, astatine. Let me draw that a little bit better. So this second to last column, group 7A as it's called, are called halogens. So fluorine, chlorine, bromine, iodine, and astatine are halogens. And then this one here, which we've already mentioned to some extent, these are called the noble gases, the very last column. All right? And we're going to sort of touch on a lot of these different categories throughout the course. We're especially going to talk a lot about these first 2 columns, the main group elements, the first 2 columns, the last 2 columns. We're not going to do too much with transition metals or metalloids in this course, but we want you to be at least a little bit aware of the categorization, because as we said, this allows us to make some predictions about their chemical properties. All right, but what we're going to mostly focus on in terms of what are called periodic trends is going to be using the periodic table to make predictions about certain key properties, not so much focusing on these categorizations, but on sort of the relative trends as we go through the periodic table and some of the key atomic properties. So we're going to talk about a few of those, 3 mainly. And the first one we're going to deal with is atomic radius. So one of the great things about the periodic table is that for these 3 properties I'm going to tell you about, plus some other things that we probably won't get to in this course, you can, based on the location of the periodic table, either the absolute location in some cases or the relative location of 2 elements, you can make predictions about these properties without actually having to know the numbers off the top of your head. So the first one we're going to talk to is atomic radius, which can, in simple forms, be thought of as just the size of the atom. Okay, is the atom smaller or bigger? Remember we talked about that, the electrons are sort of in this diffuse cloud around the nucleus. We can just define the probability of the electrons, but not the absolute position. And the atomic radius is basically how big is the electron cloud? How much space does that atom take up, including all of its electrons? Now, first we're going to talk a little bit about how it's measured or how it's defined, just to help us understand this a little bit. So, we can't measure the radius of a single atom. There's no technique that allows us to do that. There's no microscope that's powerful enough to do that. No other technique that allows us to visualize individual atoms. But what we can do is in certain types of chemical substances, metals being one major type, or certain types of compounds, we have techniques that basically allow us to measure the distance between 2 adjacent nuclei that are next to each other. We can measure the nuclei very well. We can't measure the electrons very well directly because they're so diffuse and so lightweight. But the nuclei, we can really tell where they are, and so that allows us to define an atomic radius, as it's called. So for metals, as we'll learn much later in the course, the atoms in most metals are arranged into sort of these solid packing arrangements where all the atoms are very close to each other, and so on. And what you can do then is, using different experimental techniques, which we will cover just a little bit later on in the course, we can measure the distance between 2 adjacent nuclei. So these little dots at the center are the nucleus of each metal atom. The circle represents sort of the boundary of the electron cloud as it is. And this distance here is something that we can measure experimentally. And so the metallic radius, as it's called, or more generally the atomic radius of a metal atom, is going to be 1/2 of the distance between the nuclei. All right, so again, as we go from one nucleus to the next, we're going to go through one radius and then go through a second radius to get to the second center of the next atom. So half that distance will be defined as the radius of a single atom. Okay, so that's sort of how we measure it experimentally, or sort of how we define it experimentally. But again, it's really just the radius of the electron cloud is the simple way to think about it. For nonmetals, there's different ways of doing this. So if we had some of the nonmetals occur as diatomic molecules, so like Cl2, for example, occurs naturally. So if we have two chlorine atoms next to each other, like this, we can again use different techniques to measure the distance between the nuclei, this distance there, and that's once again going to be twice the atomic radius. So experimentally, just to put some numbers on it, we don't need to know the numbers off the top of your head. This is 100 picometers. Pico is 10 to the minus 12 meters, so a very small distance. So 199 times 10 to the minus 12 meters is the distance between two chlorine atoms in Cl2, and that allows us to approximate the radius of a chlorine atom as half of that distance, just like we did for metals. So it's 199 divided by 2, so right around 100 picometers to 3 sig figs. All right, so that would allow us to get the radius of chlorine. Now, but other elements like carbon don't necessarily occur in sort of those nice simple diatomic forms, but if we had I guess carbon, you could probably do it the same way too, but let's say we had then another compound that had chlorine, which we know the radius for, and then it was bounded to another element, let's say like carbon, which we didn't know. So basically this is how all the radiuses were the radii, if I'm being grammatically correct, were pieced together. So for some elements you can measure it directly like this, where you have the same element bonded to itself, and then just half the distance is the radius. But then in other cases, we might not have the same form of the element available for all other ones, but we find another compound that has a carbon and a chlorine next to each other. We measure this distance here, which is experimentally 177 picometers, and this number, 177, is going to be the radius of the carbon atom plus the radius of the chlorine. So we have two different elements here, but we already determined the radius of chlorine, so then we can subtract to find out that the radius of carbon is 77. So basically this is how we don't have to do these calculations on homework assignments or tests, but this is how all of the atomic radius values were pieced together, by just looking at a whole bunch of different forms of elements, a whole bunch of different compounds, and the numbers that you see reported like in tables in your book or other sources are typically average values for a whole series of things that were studied. But we want to just know that the definition of atomic radius is more or less how big the atom is, how big its electron cloud is, and we can use now the periodic table to predict the relative radius of an element depending on where it's located in the periodic table. All right? Yeah? That's an experimentally determined number. So you would use a technique called X-ray diffraction or something similar to that to basically measure that number experimentally, and then you divide it by 2 to get the radius of a single chlorine atom. It's not, that number's not on the periodic table. You can't get the exact number from the periodic table, but what we're going to learn just now is that if we compare carbon to chlorine, we could figure out that chlorine's bigger than carbon, not necessarily by how much or what the exact number is, but we're going to be able to figure out relative atomic radii for different elements depending on where they are in the periodic table. It's not my number, it's the truth. It's the number that's determined experimentally. Yes, it's for that specific compound, Cl2. For any other two atoms bonded to each other, the number would be different, and the radius would then be different that you would calculate from that. This is just sort of giving you a picture of how we determine these numbers. This is not a terribly important detail. What we want to know then is that based on the location in the periodic table, we can predict the radii of different elements relative to each other. So let's think about the two different directions we can move in the periodic table, either top to bottom. So that's called going down a group. So a column of the periodic table is called a group. If we go down a group from top to bottom, let's talk about what happens. So as we talked about, the periodic table is arranged in terms of the principal quantum number n. So as we go from top to bottom, we're going from n equals 1, 2, 3, 4, 5, and so on for that sort of outer shell. So our principal quantum number increases as we go down a group. All right, and as we talked about, really starting with the Bohr model, the very simplest model we have, and it's still largely true for the more complicated quantum mechanical model that we've been dealing with now, as we go to higher and higher n values, do the electrons on average get closer to or further away from the nucleus? Further away. We talked about, really starting with the Bohr model. Each value of n is further and further away. So as you go down a group, the electrons get further away from the nucleus. And then the radius increases. So if we're comparing two elements that are related vertically in the periodic table, one on top of the other, the one that's lower down, the one that's further closer to the bottom of the periodic table is the one that's bigger, because we're adding additional shells and subshells that take the electrons further and further away from the nucleus. So that one's fairly easy to understand. The one that's a little bit less intuitive is as we go across a row or a period of the periodic table. So a period is a row of the periodic table. So as we go left to right, we're increasing the atomic number. So there's really two competing effects here as we go left to right. We're adding more electrons, but we're also adding more protons. And the electrons that we add are all going into the same subshell, so roughly the same distance from the nucleus, but now we have more protons that are holding on to those electrons. So basically, as we go left to right, the effective nuclear charge, the charge that's felt by those outer electrons, increases. The electrons we're adding are to the same subshell, and that causes the electrons to be pulled closer together. Closer to the nucleus is a better way to say that. And that causes the radius to decrease. So as we add more protons to the nucleus, if we're in the same row of the periodic table, we're still putting electrons into the same outer shell, the same n value, same principal quantum number, but we're adding more protons to the nucleus, so those outer electrons get pulled in a little bit tighter. It's not a huge effect, but it is measurable. So as you go across the row of the periodic table, the radii don't change that much, but they do progressively get a little bit smaller as you go across. So to sort of draw that out here on the periodic table, if I draw two arrows going right to left and top to bottom, these are the directions that the atomic radius increases. And for this, there's really no exceptions you have to worry about. You just use this trend to predict. We're not going to give you ones that are ambiguous in terms of their location. It's to the left, and we're typically going to pick ones that are straightforward comparisons in terms of these two trends, left to right, top to bottom. Okay? So any questions on atomic radius? Yeah. ZEFF is effective nuclear charge, Z effective. We introduced it a long time ago. So basically, when you have multi-electron atoms, the electrons that are closer to the nucleus are going to cancel out or shield some of the nuclear charge. And so the outer electrons don't feel as much of that positive charge. But as you go left to right, you're adding more protons to the nucleus, so the charge that's felt by the outer electrons gets higher and higher, and that pulls them closer in because they have a higher positive charge that's attracting them closer to the nucleus. Okay? Yep. Because that's the direction that it increases. So if we go left to right, we're increasing the number of protons and the radius shrinks. If we go right to left, it's the opposite. So I'm just drawing the trend showing the radius getting bigger, basically. So the radius gets bigger as you go from right to left. It gets smaller as you go from left to right. All right, we'll move on to the next one, which is ionization energy. We've seen this introduced a little bit. We haven't talked too much about it, but we're going to talk more about it now. So first, let's talk about what ionization energy is for an atom. It's the energy required to remove one electron from a gas phase atom. We did talk about this in the context of the Bohr model, how much energy is required to remove an electron from hydrogen. That's basically where you're taking n up to infinity, removing the electron completely. And it's going to be also defined for any other multi-electron atom, which is the amount of energy required to remove one electron. And specifically, it's from a gas phase atom. That's not terribly important, but that's just how it's defined, and that's where the periodic trends really hold true. So if we want to sort of draw out the chemical process that's happening, we're starting with a single atom in the gas phase, so the G means gas. and then we remove one electron from it. As we've already talked about, if you remove an electron from something, you create something that has a positive charge. So you're going to form a positively charged ion, also in the gas phase, and you're going to release one electron. And the change in energy for this process, how much energy we have to put into this to remove the electron, is going to be called the ionization energy. Specifically, this one is called first ionization energy because this is removing the first electron. As we'll see, we can define ionization energies for removing more and more and more electrons, depending on how many there are. The first ionization energy is removing the first electron to create a +1 ion, and that's always going to be a positive number, greater than 0. That means you have to put energy into an atom to remove an electron. That should hopefully make sense because the electron is attracted to the nucleus via those electrostatic attractions, that positive and negative charge holding onto each other. If you want to rip the electron off, you have to put energy in to pull them apart. So it's always a positive delta E, and ionization energy then being a positive number. So that's how it's defined. Now let's talk about the factors that influence the ionization energy. It's actually very closely related to radius in some sense, but it's a little bit more complicated, as we'll see. So as we go down a group, again, top to bottom on the periodic table, we said that the principal quantum number increases, which causes the radius to increase. So that's true. We're going to talk about that in the context of radius. Now what's true about ionization energy is that we're removing the electron that's furthest away. Basically the last electron that goes in is the one that comes out first. So the electron that's furthest away and the highest principal quantum number n is going to be the first one that we remove. The valence electrons, as we said they're called. And so what happens is that as the electrons get further and further away, as we go from the top to the bottom of the periodic table, the attraction to the nucleus weakens, because how strongly the electrons are attracted to the nucleus depends to some extent and inversely related to how far away they are from the nucleus. So as they get further away from the nucleus, they're going to be less attracted to the nucleus, which means it requires less energy to pull that electron off. They're held less strongly. So as the atom gets bigger, in general, the ionization energy gets smaller. Those two are sort of inversely related to each other. Now, as we go across a period, the opposite is going to be true, because as we go across a period, the effective nuclear charge, which we just clarified what that is going to increase. We're going to add more protons to the nucleus. That causes the radius to decrease. So that's what we said for radius. And because as we go from left to right across a period, we're pulling the electrons closer, they're going to be held on more strongly, and the ionization energy is going to increase. So the attraction to the nucleus increases as we go left to right, which means the ionization energy also typically increases left to right. Now, as we'll see, there's going to be some exceptions to this trend, the left to right trend, that we're going to get to in a second. But that's sort of the basic way of thinking about what normally happens. As you go top to bottom, the ionization energy decreases. As you go left to right, it increases, both those related to how strongly the electron is attracted to the nucleus. All right. So here's sort of, again, drawing it out now, the general trend for ionization energy. So as we go left to right, it increases. As we go bottom to top, it increases. So I'm drawing the arrows that indicate the increasing direction for ionization energy. But there's going to be two set parts of the periodic table where we have sort of an exception, as we would call it, a blip in the trend. So what happens is that if we're in see, I'm going to make sure I do this correctly. Group 2 and Group 5, the ionization energy is abnormally large, and the trend breaks down a little bit. All right, and this is because basically, if we're in Group 2, we have an NS2 configuration. And so anytime we have a filled subshell, NS2 or NP6 being the ones we're going to primarily deal with for the main group elements, that's a particularly stable configuration. It doesn't want to lose any of those electrons. And so NS2, if you're going to remove an electron from that, which is what ionization refers to, this is going to be a stable filled subshell, and so that makes it more difficult to remove an electron. Similarly, half-filled subshells are also stable, so if we get to Group 5 in the periodic table, that's where we have the NS2 NP3 valence configuration. To remove an electron, we'd remove one of the p electrons to get to NS2 NP2. We always take the last electron out that we put in, and here we have a stable half-filled subshell. So in both of these groups of the periodic table, the ionization energy is abnormally large. So I'm running out of room, but if we draw a little bit of a trend for that then, if this is ionization energy, and this is group number, we're gonna just do the main group. So 1, 2, 3, 4, 5, 6, 7, 8. Basically what we see is that group 1 is a relatively low ionization energy. Again, it generally increases left to right, so the general trend is going to be to increase in this direction. When we get to group 2, it's abnormally high. I'm going to draw a little bit of a guideline so I don't mess this up. So group 2 is abnormally high. Group 3 is back on the trend, but you typically see a small decrease as you go from 2 to 3. Let me draw that a little bit better. And then group 4 is sort of on the line. Then group 5 is abnormally high. Group 6 back on the line. Group 8 is also abnormally high because it's the noble gases, but it's still the highest one anyway. So let me try to line those up a little bit better. 1, 2, 3, 4, 5, 6, 7 there, 8 way off. So basically the key point is that as you go from 2 to 3, ionization energy decreases even though you're going left to right. And as you go from 5 to 6, ionization energy decreases even though you're going from left to right. So there's 2 places where the trend is not a smooth increase in ionization energy, 2 to 3 and 5 to 6. And that's because in those groups of the periodic table, you have particularly stable subshells, subshell configurations. All right. The other thing we want to talk about is we introduced the first ionization energy, and that's what you can use the periodic table to predict. So if you're going to use the location on the periodic table to predict ionization energy, that only accounts for the first ionization energy, just removing one single electron. We're going to also talk about some trends involving successive ionization energy, so as you go and remove more than one electron. So we said that the first ionization energy is defined as an atom in the gas phase going to a +1 cation, removing one electron from it. If we have the second ionization energy, what we're doing is we're removing a second electron. So we're starting with the +1 cation, where we've already removed one electron. So we always do these sort of one at a time. And so the second ionization energy, IE2 as it's abbreviated, refers to this process where we're removing one more electron and forming a +2 cation. So basically each successive ionization energy involves removing one more electron from the atom. Okay? So what's always going to be true is that as we remove more and more electrons, the ionization energy gets larger and larger. Basically, as you create a positive charge, it becomes more and more difficult to remove an additional electron. So you're always going to have this trend. They're always going to increase as you go from 1 to 2 to 3 and so on. Okay? So no matter how many ionization energies you're considering for an atom, it's going to get higher and higher and higher each one you go along. And that's because it's harder to remove an electron from a cation. So as we start removing electrons and forming positively charged cations, it gets more and more difficult to remove those electrons as we go along, right? So that's always going to be true. But then there's also, what you'll notice is, let's look at the ionization energies for nitrogen and oxygen. These are real numbers now in megajoules per mole. And so what we're going to look at is how they sort of change. So as we go from 1 to 2 to 3 and so on. So if you see for nitrogen, it gradually goes up. It goes from 1.40 to 2.86, goes up a little bit more to 4.58, goes up a little bit more to 7.48, goes up a little bit more to 9.54. So 9.44. All the ionization energies are increasing, but then we see from 5 to 6, there's a huge jump. We go from 9.44 to 53.27, just a huge spike in ionization energy there. And then if we go for oxygen, we see that, again, gradual increases, 1.31. Oxygen is a little bit lower because of that trend, that exception in the trend, group 5 to group 6. And then we go 3.39, 5.3, 7.47, 10.98, 13.33, gradual increase, and then boom, huge jump at 7, going all the way up to 71.33. So we see at some point you get to a place where the ionization energy jumps by a huge amount, and that's going to occur after you've removed all of the valence electrons. So nitrogen is group 5. It has a valence configuration of 2s2, 2p3. So after we've removed the first 5 valence electrons, we have to start removing core electrons, the ones that are even closer, and that becomes increasingly very difficult to do. So basically you're going to see it in the same for oxygen, 2s2, 2p4 valence configuration. 6 valence electrons, so the first 6 ionization energies are going to sort of gradually increase, and then to do a 7th ionization, removing a core electron, we see that it goes up by a huge amount because now we have to start removing core electrons. So you're going to always see these huge jumps in ionization energy when you get to the core electrons. And basically it's hard to remove those core electrons. All right, so it's comparatively easy to remove valence electrons, relatively low ionization energies, extremely difficult to remove core electrons. All right, and then the last thing we're probably going to end up covering today is electron affinity. So this is the last periodic trend, the last property we want you to know. It's related to ionization energy, but it's sort of the opposite process. So ionization energy is the process of removing an electron from an atom. Electron affinity is the process of adding an extra electron to an atom. So it's the energy change that accompanies the addition of one electron. So in this case, what we're doing is we're starting again with a gas phase atom. We're always defining these in the gas phase. We this time add an electron to it to form a negatively charged ion. And the delta E for this process, the energy change as we add one electron to the atom, is referred to as the electron affinity, abbreviated as EA. And again, you can have first, second, third, and so on, which is referring to the electron affinity for adding 1, 2, 3, and however many other electrons. This is usually a negative number, the first ionization energy anyway. So normally it's favorable energetically. You basically lose energy to add an electron. You're forming a new attraction between the electron and the nucleus, the electron that you've added and the nucleus that's in the center of the atom. That generally results in a decrease in energy for the system, but it's sometimes positive, and we're not going to worry too much about the signs. We just want to know again the relative magnitude of them. All right, so again, the factors that influence it are very similar to the factors that influence ionization energy. The atomic size, the radius. So the larger atoms have smaller, and when we say smaller, we mean less negative. So typically we're talking about the magnitude of the electron affinity. So as the atom gets larger, the electron that we're adding is further away, so the attraction to the nucleus is weaker, so you basically gain or lose less energy by doing that. And then also the effective nuclear charge. So really the same things that affect ionization energy also affect electron affinity. So in most cases, as you increase the effective nuclear charge going left to right, that leads to larger, or what we say is more negative, electron affinities. Okay, so the trend is very similar to ionization energy. It actually has the same periodic trend. It increases as you go from the bottom to the top of the periodic table, and it increases as you move left to right. That again is the basic trend. So we'll draw that out here, increasing bottom to the top, increasing left to right. And again, to be clear on what we mean by terminology, electron affinity is technically a negative number, so when we say increasing, we mean a larger negative number, more negative. All right? It basically wants an electron more. This one also has some exceptions. The exceptions are actually the same as we saw before. So in group 2 and group 5, you're going to have abnormally, in this case, low electron affinities. Okay? So it's sort of the same places where the trend breaks down, and it's the same reason. It's because those configurations, group 2 being S2, group 5 being S2P3, those are abnormally stable configurations, and so it doesn't want to add any more electrons either. It wants to stay exactly how many electrons it has, not add or lose electrons. And so in this case, it doesn't want electrons, so it has a low electron affinity. We should also mention that the noble gases, we don't really consider those for electron affinity. They have no electron affinity because, as we'll talk about a little bit more next time, the S2P6 configuration, the noble gas configuration, is the most stable of all. So they don't want to have anything to do with losing or gaining electrons. So we don't even think about electron affinity for noble gases. It's non-existent. But for the rest of the group 1 through 7, we have the basic trend of increasing left to right. And if we draw that out, what we're going to see, this is the electron affinity, sort of the absolute value of it, if you will, because it's technically a negative number, but the magnitude of it. And this is, again, group number 1, 2, 3, 4, 5. We'll just go to 7 in this case. The general trend is to increase left to right, but what we'll see is that group 2 is abnormally low, and then we have group 3 and group 4 sort of on the trend, group 5 abnormally low, group 6 and group 7. You're never going to jump 2 rows, two things. So basically, group 5 will be below group 4. It'll dip down a little bit, but not below group 3. So it's only going to be basically a dip in one step. So it's going to go 4 to 5 is going to decrease, and it's going to go back up. And again, the blips in the trend are at the same spot, group 2 and group 5, because of the stable configurations. But this time they don't want to add electrons, so that makes the electron affinity lower than the other elements around it. All right, so next time we're going to move into chapter 3 and start talking about the formation of ions and ionic compounds.